Thank you. It's a pleasure being invited to this. I'm feeling somewhat uncomfortable here being bookended between two people who actually know a lot about the policy environment here with respect to biosecurity and bioinvasions. My talk is in contrast going to be somewhat narrow and technical, but I hope I can convince you by the end that, that what I'm addressing here is sort of fundamental to the question of policy issues that concern bioinvasions in particular. Surprisingly, economists haven't, in some sense, done the groundwork for this particular problem, and what I'm going to talk about is our attempt to do that. So this is some work that was motivated by a thesis that one of my students, Becky Apanchin-Neal, completed last year. She's now working for Resources for the Future, which is an environmental resource economics think tank in Washington, D.C. And this problem started out being, the focus of this thesis was on star thistle, which is an invasive plant in California that basically reduces the productivity of rangeland pretty much in proportion to the amount invaded. It's a serious problem. Goats won't even eat this stuff, and cows certainly won't eat it. So it's a serious problem. It fit into a longer-term interest of mine, though, because I've been thinking about, for the last 10 years, a particular class of problems that economists haven't paid very much attention to, and they are what I call spatial dynamic problems. We've spent a lot of time developing the apparatus to handle dynamic problems, where the issue is how to use things up over time. We have ideas that go back to the 1700s about how things are located over the landscape, but in fact, there's a whole set of problems that we haven't paid much attention to that involve sort of the combination of spatial and dynamic processes themselves. Forest fire is an obvious one. It spreads. Understanding its spread is complicated and difficult to do. Forest fire will be influenced by humans in several ways. It will be influenced by the fact that if you have a forest where people have summer cabins, whether they put defensible space around their cabin or not will affect the way a forest fire spreads. It will be affected by the policies that are in fact imposed to try to control the forest fire. We've got backfire methods and aerial spraying, a whole range of things that influence the pattern that evolves over space and time. Floods, you've just experienced a spatial dynamic process in the floods that you've experienced. Animals, disease problems, human disease problems are all examples of things that spread over time and space, acrophodynamics, etc. And I see basically the problem of bioinvasions as one case of this sort of class of problems. So I want to put up an animation here that really depicts the essence of this problem and that sort of motivates our discussion of the economics of addressing this kind of problem. And this is it's going to be a map of the spread of rabies in the fox population in Switzerland, starting back in the 1960s. And what we'll see with a bunch of red dots is this pattern that evolves over space and time, which itself is driven by dynamic factors. It's driven by births, deaths, growth of a population in a given location, but it's also driven by spatial processes, namely the interaction between infected fox populations and those that are susceptible. So as fox populations trade saliva or bite each other, the thing spreads over space. And the way it spreads over space is in part dictated by the nature of space itself, mountain ranges, rivers, highways, a whole range of things like that. And, no. All right. This is quite important because this is quite a beautiful animation. That's a bummer. Imagine the map here. I mean, basically what happens is that, as I say, these particular processes that govern how things spread over the landscape, we see the pattern of uncontrolled spread of this rabies vaccine, and then of the rabies epidemic, and then in the 1970s, the Swiss intervened in the system and began to try to control it. The way they controlled it was to put out vaccinated chicken necks that had vaccine in them. And in contrast to the old way of controlling rabies, where you killed rabid animals, in this case what they did was vaccinate the susceptible animals so that they wouldn't, in fact, pass the disease on to other susceptible animals. And so they began to put out swaths of vaccine-laden chicken necks all over the landscape in Switzerland, and it backed the population up, and the population came back in as there were new infestations from the borders, and they kept pushing this back. And so, important thing is that this, I mean, unfortunately, this is not going to work, but it shows how these processes unfold, and it poses the question of, all right, if this is what we're facing, how do we in fact control that? Where do we put out the controls? How intensively do we put them out? When do we put them out? So the basic questions here for economists and for the policy scene here is, how is this going to evolve if we don't do anything? If we decide to do something about it, what should we do? How much control should we employ? How intensively? When, in terms of timing? And more importantly, where do we put controls out in space? Other issues here are sort of how does the characteristic of the landscape that you're talking about affect the nature of the optimal control? And as economists, we're interested in how to design institutions to control these kinds of spatial dynamic processes. So what we're looking at here is it is the process of trying to control something once it's established in the landscape. The literature, a lot of the literature focuses on how to stop something before it enters into the landscape. The literature also, for the most part, aggregates over and looks at a population as a whole rather than looking at where a population is located. What's different about what we're doing is that we're looking at a situation where an invasion has established itself, and then the question is, where do we put our efforts over time, and importantly, over space? So, I mean, what we've done here is basically develop what I call a small, simple model, which tries to capture the essence of these kinds of processes. And our idea here is to build up some intuition about how space matters for this kind of problem, and to understand how the nature, the qualitative and quantitative nature of the optimal control policy itself is influenced by biological parameters, by space, by heterogeneity of space, and by economic parameters. So the idea here is that that's a piece of a grid of land here that's infested at the beginning. We just assume that we discover that there's an infestation of something. In this case, that's a picture of star thistle. And if we do nothing, it'll spread in some particular way, a step at a time. It'll spread in a chessboard fashion, what's called root contiguity. So it'll spread to adjacent pieces of land and continue to do this across the landscape if we do nothing. So what we've imposed on that then is the possibility of controlling. One type of control is where you prevent the spread by imposing some sort of barrier, spraying, pulling the weeds, doing something that in fact prevents the infestation onto adjacent patches. And we've got that embedded in this model, so it costs you something, and it costs you something in proportion to the number of borders that you're trying to control. Another possibility is that you simply go in and eradicate or clear out the invasion, which will cost you something as a lump sum also. And the essence of this problem really is how do we minimize the sum of the discounted damages and control costs over time and over space when there are some damages that are associated with each patch's infestation, some border control costs if you choose that particular policy, and some clearing costs if you choose that particular policy. This is a difficult problem, as it turns out, and surprisingly, it hasn't been solved in the literature. There's a reason, I think, and that is because ordinary dynamic problems that we're used to solving involve solving a solution where a state variable evolves over time, and the nature of that particular problem is characterized by a system of differential equations. These kinds of spatial dynamic processes, in contrast, have to be characterized by a system of partial differential equations, and the way things evolve over time depends on not only what's going on at the point in space, but at the point in time, but also on what's happening around the particular population that you're talking about in space. So these are hard problems. They're hard to analyze mathematically. They're also hard to deal with numerically. What you would think you might do is to use a common method that we use for solving dynamic problems, and that is to use dynamic programming. And that involves basically looking at the last stage, optimizing it, stepping back, asking, okay, if we know what to do in the last stage, what do we do in the stage next to the last stage, and so on. And that often involves enumerating all the different possibilities. And embarrassingly enough, we thought that we could use that method for this particular problem, which is really stupid in hindsight because it's worse than a dynamic problem. It's got space in addition to time, and so it just magnifies what's called the curse of dimensionality, which involves sort of using computer power to analyze all the different possibilities. So, for example, if you only were dealing with a 5x5 patch or configuration of space, you would have to, if you wanted to enumerate all the possibilities, look at 33 million different opportunities just for the last stage of the problem. It blossoms bigger than that, and right now I think the extent of our ability to solve dynamic problems is equivalent to being able to solve about a 13 by 13 landscape in the context of our problem.